So before we get started doing example 1, I wanted to show you some pictures of some cross sections that you might actually be able to help visualize a little better exactly what is happening. So here's a circular base, and notice the cross sections are triangles. If I focus on this one, notice that again it's a circular base, but the cross sections are squares. And then this one actually has an animation to it that I'm going to struggle with, and that the base is a square and we're generating cross sections that are also squares. So I thought those were all kind of interesting. Of course, you could go to Google Images and type in cross section volumes, and you would come up with a whole bunch of examples that would help you visualize it. So here I've drawn a circular base with a radius of 1, and I've sliced out one particular cross section, which is an equilateral triangle. And if you remember, these are how I'd find the measurements for each of the lengths that I'm going to need if the entire side or the entire base is length b. If you remember from geometry, the formula for your prism, for volume of a prism, is big B times h. Now, if you go back and look at the picture of the circular base with the triangular cross sections, think of this as we have a whole bunch of triangular slices, but they go from a little tiny slice and then they keep getting progressively bigger as we go across the circle, and then they would get smaller again on the other side. So it's like I'm taking a stack of triangles that's going from small to big and then big to small on the back side of it. Which means, of course, that the area of my base is this equilateral triangle. So big B is going to be 1/2 the base of the triangle times the height of the triangle. And now I'm going to draw a top view of my circle. Okay, so now if you notice up at the top, I wrote the equation for my circle, x squared plus y squared equals 1, since it had a radius of 1. And then I solved it for y, which we would know that the top half of the circle would be the positive version, and the bottom half of the circle would be the negative version. Now, this cross-sectional slice right here in orange would be the base on my triangle. And so I'm going to have to do top minus bottom to get that little base. So the top would be the positive square root, and then I'd subtract the bottom, which would be the negative square root. So I'm going to end up, of course, adding these, which means the base of all my triangles is 2 times the quantity of the square root 1 minus x squared. Now, if you notice in my equilateral triangle drawing, so whatever this entire base is, of course that would have been big B, the height of that equilateral triangle by my 30, 60, 90 relationships is that same base multiplied by square root of 3 over 2. Well, I already found the little base over here, so that now means that my height for all of my triangular cross sections is simply that same base times the square root of 3 over 2. And of course, those 2's are going to cancel out. So I'm ready to integrate using the area of my cross section, which is the 1/2 the base times the height for all my triangles. So I'm going to multiply my little base and my little height. And of course, here's everything substituted in. So I've substituted in little base and my height, and there's the 1/2 because I'm working on a triangle. And this will simplify to, and since I'm integrating with respect to x, I have to look at the farthest x bound, which is -1, and the farthest right, which is 1.